Hey class. So we talked about energy before, the ability to cause change or to do work. Today we're going to talk about something closely related to that, which is momentum. You might have used the word or heard the word before, like for example, oh, that football player had momentum, or we're gaining momentum in this project. But what does that mean in science? Remember how we had a different definition for work in science when we discuss energy? In this particular case, momentum also has its own meaning in science. So, what does it mean? Momentum is a way of measuring how much motion something has. It depends on two things. Number one, how heavy the object is, its mass. And number two, how fast it's moving, its velocity, speed plus direction, right? But here's a super simple definition. Momentum is moving power. It's how much push an object has because of its mass and its speed, right? So let's say I throw a tennis ball at you. It's light, but if I throw it fast, it could sting when it hits your arm. Now imagine a bowling ball rolling slowly towards your feet. It might also hurt if it bumps into your toes. Both feel like they've got some oomph going on. That's momentum. So let me ask you, which one has more momentum? The light, fast tennis ball headed your way, or the heavy, slow bowling ball rolling your way? Well, it depends on the combination of both their mass and the speed. Okay, the tennis ball is light and fast. The bowling ball is heavy and slow. And it could be that their momentum could actually be exactly the same because momentum, remember, is a product of speed, velocity, and mass. Take, for example, I'm just going to put numbers out there for you. Say the tennis ball is a 2 and its velocity is a 3. So that's a 5. 2 plus 3 is 5. But then let's say the bowling ball is also is a 3 and its velocity is a 2, or the bowling ball is a 4 and its velocity is a 1, they all add up to 5. So in terms of momentum, they have the identical number. Always remember, however, that that doesn't necessarily mean that in every combination or every example, there's an absolutely equal pairing, but it could work out that way for you. Lucky you. Okay, so if I was going to write the formula on the board, I would write P equals M times V. Why P? I don't know. That's just a physics thing. They picked the letter P for momentum, I guess, because M is just being taken up in so many different ways. So P equals M, as in Mary, times V, as in victory. So that's all lowercase. So that's your formula. By the way, if something isn't moving, its momentum is zero. Once it starts rolling, flying, or crashing, momentum kicks in. Why do I tell you that its momentum would be zero if it isn't moving? Because you could say to me, well, teach, P equals M times V, okay? So, and it's got a lot of mass, but it's got no velocity, but it's still got a lot of mass. Well, because you have to have both. You have to have both in order for the P to kick in. Well, let's think about what happens when there's a collision. When two things collide, that momentum just doesn't disappear. Even if, like say, two cars are totaled, they hit each other, boom, head on, they're totaled, and everything comes to a stop. Scientists know that the momentum before the crash equals the momentum after that crash. That is called the law of conservation of momentum. So, in other words, you don't lose momentum, it just gets redistributed. So, where does it go? I mean, obviously, the two objects, i.e., the cars, have come to a complete stop. They're totaled, they're not moving. All that momentum, that motion, once the car stopped, they hit themselves on, went into flying debris, went into the force that crushed the car, went into the sound of the crash. Remember sound energy? and it went into pushing onto other objects or things, maybe a side rail, maybe the road, and unfortunately, maybe the drivers and the passengers, etc. So momentum doesn't just vanish, it courses through the system. And then scientists and engineers are taking all that information, for example, to figure out how to cause that momentum to slow down as it's coursing through the system. What we mean by the system here is the two vehicles colliding or the two objects colliding when they meet each other. That is, in effect, the system. It's a confined area or a confined space where this momentum is happening. So it's a system. So as the momentum forces through the system, if it goes too fast, it's pretty devastating. But if scientists and engineers can figure out a way to slow down the effects of that impact when the two vehicles hit each other, then there's a higher chance that the passengers and the driver can survive the impact. And that's why you have in cars, they have what they call crumple zones. Almost looks like plastic on a car. It's very intelligent and it's counterintuitive in a way because you think, oh, if I have a vehicle that's all metal, then obviously I'm going to have better chances if I'm involved in a crash. But modern technology, the technology that's in place today, after so much data that has been studied by engineers and scientists, is that they've learned that if they have different material that could kind of absorb the force of the impact, meaning the momentum that impacted the vehicles, into this kind of material that can crumple, it tends to slow down the momentum that's coursing through the system. Also, seatbelts. When you're wearing seatbelts and airbags, also help spread out that momentum. So it doesn't just go into one area like the passengers and whatnot. Also, strong cabin frames help protect the passengers while the momentum is coursing through the system, hopefully through the crumple zones. And the seatbelts also help hold the passengers from propelling forward on impact, and the airbags do the same thing. All these combinations of things, the crumple zones, the seatbelts, the airbags, strong cabins, and everything helps slow down the momentum's transfer as it's coursing through the system. This will mean less force equals less injury. But just to help you understand, momentum doesn't just keep going. Even though it gets distributed to different parts, through the road, through sound, through everything, it doesn't mean it's just going to continue forever. Momentum can't be stopped necessarily in the moment, it can be slowed down. However, once it courses through the system, you're done. And when you slow it down, momentum, it takes longer to reach a stop, but it's also gentler, the way the force comes to a stop. But when it's an immediate impact with hardly anything to slow down the course of it, then it'll come to an immediate stop. It has a high impact, and well, that's not very good. Okay, so think about it. You know the analogy. It's like sliding into home plate when you're a baseball player. If you suddenly stop at the home plate, you'll get hurt. But if you slide in and slow down, you'll make it in easier. And that's exactly what cars are designed to do. They just slide into a safe stop, hopefully. And you think of an example where something light is moving fast and something heavy is moving slow, but they would both feel the same when they hit you. Well, to give you an example of something that shows equal momentum, say different masses and speeds, let's just off the top of our heads come up with an example. Let's say example one would be a soccer ball versus a bowling ball. Probably in terms of size wise, they're the same. But mass wise, obviously they're going to be different. Say a soccer ball might weigh half a kilo or a little bit over a pound, whereas a bowling ball weighs 5 kilos or 11 pounds. You take a soccer ball weighing half a kilo and it goes to the speed of 10 meters per second, then your momentum is 5.5 kilogram meters per second. And then you have a bowling ball that weighs 5 kilos, but its momentum is only 1 meter per second. Well, 5 times 1 is also 5, so it's the same. So we've got a half kilo, the soccer ball, times 10 equals 5, and 5 kilos times 1 equals 5 for the bowling ball. So the soccer ball is light but fast, and the bowling ball is heavy but slow, but both have 5 kilogram meters per second of momentum. So they carry the same amount of push, just in different ways. All right, so let's look at example number 2. You got a big truck and a small car. So the truck weighs about 6,000 kilograms, right? Its speed is at 2 meters per second. So the momentum is 6,000 times its speed, which is 2. So that'll give you 12,000 kilogram meters per second. Then you've got the small car. Small car weighs 1,200 kilograms, but it's going faster at 10 meters per second. And its momentum, however, when you multiply 1,200 times 10, it's 12,000 kilograms per meters per second. Okay, so even though the truck is moving slow, its mass gives a serious momentum. So heavy, right? And the small car is much lighter, but it's going faster. But because of the fact that it's lighter, it kind of takes away from the speed. Whereas with the truck, it's going slow, but because it's so much heavier, it's also taking away from speed, but it's making up for it in mass. So they both have the same momentum, but a totally different driving experience, you could say. All right, so let's go for number 3. So you've got a fast baseball versus a slow cannonball. Okay. The baseball weighs about 150 grams or 0.15 kilograms. And its speed, well, it's hurling at 60 meters per second. That's pretty fast. You've got a good arm. So if you take the 0.15 and you multiply it by 60, it gives you 9 kilogram meters per second. Now, let's say the cannonball has that big mass. It's even heavier than the bowling ball. This is a 9 kilogram ball, but it's moving really slow, like the bowling ball previously. It's only 1 meter per second, but you take 9 times 1, it's 9. So here we go. The baseball is 9, the cannonball is 9. Which would you rather be hit by, right? Okay, so same momentum, very different outcome. Because energy and impact feel different, even if the momentum is equal. So let me say that again. Same momentum, very different outcome, because energy and impact feel different, even if the momentum is equal. So let's do some quick scenarios. So you have number 1, a paper airplane flies really fast. A heavy book slides across the table slowly. So which one has more momentum? Well, we can't keep doing equal momentum scenarios forever. So let's see. It depends on a lot of things. So let's try to figure this one out. Even though we don't have exact weights and stuff, so which one has more mass? Well, that's an easy one. It's the book. Which one do you think would be going faster, the book or the paper airplane? So which factor do you think matters more? Paper airplane speed or the book's weight? Well, we can't really measure the exact speed here, but we know 2 things. The airplane is light and fast, and the book is heavy and slow. So momentum depends on both things, right? Mass times velocity. So it's possible if the speeds and masses balance that their momentum could be the same. We're not really sure in this one unless we're sitting there really scientific like. So physics isn't always about exact numbers, but it's about understanding how things affect each other. So we just reason through it. And reasoning is still just as powerful as math. So let's go to number 2. Number 2, you're riding a scooter pretty slow, but a fast running dog is coming right at you. Could you have equal momentum? So let's compare. Hypothesize mass and speed to the dogs, your mass and speed to the dogs. Okay, so let's say you're riding the scooter slowly down the sidewalk. Suddenly, the big dog, maybe it's like a Great Dane or a Newfoundland, is running straight towards you, right? Who has more mass, you or the dog? Well, that depends. The Newfoundland can weigh up to 70 kilos. So maybe it's close to you, maybe it's not. Who's going faster? Well, definitely the dog. We just said that you were going kind of slow on your scooter, but the dog is charging. So then who has more momentum? Well, again, we go back to the exact numbers. But in this case, it seems pretty clear. It's probably going to be the dog since you're like, kind of bony and everything. And it's going fast and it's heavy, whereas you're lighter and going slow, right? So it's pretty much a no brainer. Momentum gets transferred upon impact. If the dog has more momentum, which most likely it does than you do, it means you get knocked off the scooter. But if you both are kind of similar, it could be a messy situation because, again, the momentum has to course through the system. And as far as I know, you don't have crumple zones on your body. So think about it. If instead of a big dog, it could be a little dog, well, then poor little dog, right? So, all right, so one more. Two bumper cars at a fair crash. One is much heavier than the other, but the other one is zooming along. What determines who gets pushed back more? They both bump into each other, but they have these big rubber bumpers. But which one gets pushed back even more or rebounds even more? So which one do you think it is? Same thing, same thing. You have the kind of guesstimate as to what's going on and make a call. And that's how you're doing. Unless you want to really specifically going to a lab and research the exact speed, the exact weight of those cars and everything. Based on the scenario that we've got with just what we have or just words and our imagination, we have to assume that the bigger one is probably going about the same rate because it's an electric bumper car. And as far as I know, all bumper cars go at the same speed. I mean, I've never seen one with a dial for speed. So we have to assume they all go at the same speed. They're heading in the same, or at least they're heading in directions towards each other. Boom, they impact. Because of the rubber bumper, it kind of pushes the momentum back. And the lighter one should be the one that goes back even more because the bigger one put more force into it, more momentum transferred, more if it's momentum into the smaller bumper car. All right. Well, I hope that clears things up a bit for you. So let me know by commenting below